So, during this lecture, we will talk about more applications of the Laplace transform. As we have seen during the past lecture, the Laplace transform has some interesting properties. Those properties are such that, for example, exponentials of time are transformed into rational fractions. In the same vein, we have seen that the Laplace transform of a derivative is a constant s times the Laplace transform of the original function. We have seen plenty of other things like that. And by now, I would like to cover additional properties. These properties will lead us to seeing the Laplace transform as a very convenient mechanism to solve linear differential equations. We will see a few examples of that, and those examples hopefully will serve as the basis for what follows in AE 3515. So, what I want to do is bring back to your memory the notion of the Laplace transform. By the way, I would like to thank the person who indicated that I should be using Paint rather than Microsoft PowerPoint as a way to do nice drawings. So, given f, I said given f. Okay, let's draw something. So, this is not what I wanted. Let's look for something else. Okay. Maybe. Okay. Let's do this, that. Let's erase everything. And let's try again. So, given a function f, okay, that takes t and maps it onto f of t, remember that t is time, then the Laplace transform of f, which is the function of the complex variable s, is the integral from 0 to infinity of e to the minus st f of t dt. Now, what I am interested in looking at now is the effect of the Laplace transform on new quantities. So one of these is what happens if I take f of t and I multiply it by e to the minus at. Okay, I'm interested in computing the Laplace transform of this. As before, it is the integral from 0 to infinity of e to the minus st, and then we have f of t e to the minus at dt, which is also the integral from 0 to infinity of e to the minus s plus a t f of t dt, which is Laplace transform of f applied to the variable s plus a. So the Laplace transform of a function times an exponential is just the Laplace transform of the function applied to s plus a. Now, let's look at something similar. Which is the time delay. Okay. So the time delay is if you are given a quantity tau, okay, the time delay function it takes f, so delay of f is itself a function of time, which is f of t minus tau. Okay, so delay of f is a function of time, and the value at time t is f of t minus tau. So just for you to be convinced about the fact that this is the traditional notion of delay, here is f of t, okay, and delay of f of t, so I call it t. If I put t minus tau here, it just says that the value of the function for delay of f of t, okay, is just the value of the function as it was before. So here it comes about there, there it's about there, there goes about here, and you see that when you join all the things, you basically obtain a shifted version of f to the right. So time delays, I'm sorry, let's get back here. Time delays are very important in dynamical systems. Okay? So, considering this time delay function, And okay, so I'm going to try something here. Oh, no. Delete everything. I am interested in computing the Laplace transform of the delay, which I will call delay tau, to remind us that there is a delay tau, applied to the function f. By definition, it is the integral from 0 to infinity of delay of f. I put the little tau index here to remind us that the delay has value tau, e to the minus st dt. Now, if I go back, I remember that delay tau of f is just f of t minus tau, so that becomes f of t minus tau e to the minus st dt. Now, we can change the bounds here. Remember that if this is, first of all, f we assume is 0 before time began. Okay, so it's something like this. Okay, so if this is it, okay, then f of t minus tau is going to basically do that. Okay, so we have this period here over which f is 0. And so what we can say is that this is equal to the integral from 0 to infinity let me replace the 0 by tau of f of t minus tau e to the minus st dt. Now, if you go further, the integral from tau to infinity of f of t minus tau dt, okay, if we do a change of variable, which is u is equal to t minus tau, okay, then this guy will also be equal to the integral from 0 to infinity of f of t, and then here we replace the e to the minus st by e to the minus s times, well, t, which is u plus tau. And so what we end up having is that this is equivalent and equal to e to the minus s tau integral from 0 to infinity of f of t e to the minus s u. Oh, sorry, this is not t here, this is u, okay, because we did the change of variable. And so it is e to the minus s tau times the Laplace transform of f. Okay, so we end up with the statement that this guy must be equal to e to the minus s tau times the Laplace transform of f. In a way, you see that this is very similar to the Laplace transform of e to the some variable times f, which becomes a shift in the frequency domain, and then this guy is the opposite. Whenever the delay, there is a shift in the time domain. In the Laplace transform domain, it becomes an exponential. Now, I said S is in the frequency domain. Well, so e to the minus s tau, when we compute this exponential, we assume that this quantity here is non-dimensional. S times tau is non-dimensional. Okay? So, if tau has dimension of time, then S has the dimension of 1 over time. And what that means is that indeed S has the dimension of a frequency. A frequency is something per second, like a number of blinks per second, a number of oscillations per second, a number of whatever per second. And so S indeed has the dimension of a frequency. Often we will see later that we will use radians per second as that unit of frequency. Radians don't have a unit, seconds have the unit of seconds, so this is a unit of frequency. Okay? All right. So now I would like to cover a couple of interesting theorems, which are the initial value theorem and the final value theorem. Those theorems relate the values of f and its Laplace transform f at 0 and infinity respectively. So, first of all, I would like to talk about the Laplace transform of f. So the Laplace transform of f is simply, as we have seen before, the integral from 0 to infinity of e to the s times t f of t dt. So I'm interested in what happens when s tends towards 0. Well, so when s tends towards 0, e to the st tends towards 1. And so this tends towards the integral from 0 to infinity of f of t dt. So we can say that limit of L of f of s when s tends towards 0 is integral from 0 to infinity of f of t dt. Now, what we can try is, instead of taking f of s, okay, we're going to try and take s times f of s, okay, s times the Laplace transform of f applied to s. Then what do we get? Well, you may remember that we had some interesting views on the value of the Laplace transform of f prime. Right? If I remember, the Laplace transform of f prime was simply integral from 0 to infinity of e to the st times f prime of t dt. Okay, and then we did an integration by parts, and that would get us to let's see, what was it? So we have a prime here, so that get us to e to the st times f of t taken between 0 and infinity. Okay, and then, oh, I forgot the minus here. Okay, just like I forgot the minus there. Woo. And then so we got e to the minus st here, f of t, blah blah blah. Okay, and then we said plus s times the integral from 0 to infinity of f of t times e to the minus st dt. Okay, now this guy was equal to, hold on a second, this guy was equal to minus f of 0. Okay, and this guy is s times the Laplace transform of f. Now here we have s times the Laplace transform of f. So what do we get? We get that this is equal to f of 0 plus the Laplace transform of f prime. Okay. Now, so s times the Laplace transform of f applies to s is that. Now, let us look at this Laplace transform of f prime when s tends towards 0. When s tends towards 0, the Laplace transform of f prime is limit when s tends towards 0 of the integral from 0 to infinity of e to the minus st f prime of t dt. Now we know that the limit of this will be, when s tends towards 0, the limit of this will be the integral from 0 to infinity of f of t dt. Sorry, f prime of t dt, which is f of infinity minus f of 0. So this guy here, when s tends towards 0, becomes f of 0 plus f of infinity minus f of 0. So I obtain the following theorem. Oh, by the way, of course, this is equal to f of infinity. We obtain the following theorem, that limit when s tends towards 0 of s times f of s is equal to f of infinity. Interesting, hey? So you can call it initial or final value theorem. I forgot. But that is true. Okay? That is true. Now, we can likewise try and see what happens when we let s go to infinity, or we let t here go down to 0. Okay? So we'll remember this theorem here, and we're just going to sort of erase everything because it's getting a little busy here. And I'm going to rewrite what we had before, okay, which is that limit s tends towards 0 of s times f of s is equal to limit when t tends towards infinity of f of t. Okay. So that's one cool theorem. The other one involves s going towards infinity or t going towards 0. So, I mean, look at this. Possibly the best way to do that is by looking back at the Laplace transform. So we have f of s is equal to integral from 0 to infinity of e to the st times f of t, oh, by the way, I always forget that minus, times f of t dt. Okay. And we are asking about what the value of this thing is when s turns towards infinity. Okay. So for that purpose, I need to think for a second. Possibly the way to look at this is by doing an integration by part again. We're going to try this. Okay? We're going to say that this is something that we integrate here and something that whose derivative we take there. So we can write this as minus 1 over s times e to the minus st f of t taken between 0 and infinity, so we take the value at infinity minus the value at 0, plus 1 over s times integral from 0 to infinity of e to the minus st times f prime of t dt. Okay? Now, the hope is that this guy will stay bounded, this guy will go to 0 when s gets big, and so there remain these guys. So we get that this is minus 1 over s times e to the minus st f of t when t goes to infinity, this guy is 0. Plus 1 over s times f of t, f of 0. Okay? So we remember this guy. Now let's deal with this guy. Now, I claim this guy is bounded. Okay? That would take a little bit of too much of time, but trust me, this guy is bounded. Divide by s in front of it, and it tends towards 0. So it tends towards 0, I said. Okay. So what we're left with is that when s tends towards infinity, f of s looks like about 1 over s times f of 0. Or in other terms, f of 0 looks like s times f of s. Limit when s tends to 1 infinity of s f of s is equal to f of 0. And that concludes our second theorem. Right? So limit when s tends towards 0 of s f of s is the limit of f of t when t tends towards infinity, and vice versa. When s tends towards infinity, this guy tends towards f of 0. Okay? I think it's quite remarkable. And these are the initial and final value theorem. So, we are getting very well equipped here. Okay? We are getting very well equipped. We have a variety of tools handy in order to compute not only the Laplace transforms, but what the Laplace transform do to most of the functions we're interested in, what they do to limits of functions, etc., etc., etc. So, what we should be really doing at this point is now try and using it for specific examples. The best thing I can think about is currently differential equations that would get us very quickly into the heat of the action. I want to show you how to solve differential equations very quickly using Laplace and inverse Laplace transforms. So for that, I'm going to erase this thing and get restarted somehow. So how do I do that? Well, I'm going to start with an example. Probably most of you know how to solve the following differential equation. X dot is equal to a times x, and x of 0 is equal to x0. The answer is x equals x0 e to the at. Okay, that's standard DFQ. Now I'm going to show you how we can solve not only these kind of equations, but much more complicated equations without too much of a hassle. Okay, what we're going to do is we're going to take the Laplace transform. Okay, we're going to take the Laplace transform, and we're going to look at what happens. So we're going to take the Laplace transform of x dot. Now x dot is the derivative of x. So we know that the Laplace transform of x dot is going to be minus x0 plus s times the Laplace transform of x. In order to get simpler, we probably should write something like x equals the Laplace transform of x. Otherwise, this thing will never end. So, we can rewrite this as the Laplace transform of x dot is minus x0 plus s times x. Now the right hand side tells us that since x dot equals ax, the Laplace transform of x dot must be equal to the Laplace transform of ax, which is a times x. So what we get simply is by factoring out things and putting things, equal things onto the same side, x times a minus s equals x0. Or in other terms, x equal minus x0, or x equals x0 divided by s minus a. Now we know that 1 over s minus a is the Laplace transform of e to the at. Therefore, we know that x must be equal to x0 e to the at, which matches this solution that we knew from our differential equation days. You may have seen this already, but it never hurts to see it again. Okay? Now, the very interesting thing is that you can use it to solve more complex differential equations without that much of a hassle. So what we're going to do is, for example, take a second order differential equation. Okay. Let me erase all this and delete. And we're going to look, as I said, into a second order DFQ. Linear. That's very important. So let's look at the following. X double dot plus 2x dot plus x is equal to 0 with the initial condition x of 0 is equal to 1, x of 1, and x dot of 0 is equal to, I don't know, 3. Okay. So first we take the Laplace transform. Okay. And the Laplace transform of x double dot is going to be what? Well, yeah, it's getting interesting. The Laplace transform of x double dot is going to be, the Laplace transform is going to be minus x dot of 0 plus s times the Laplace transform of x dot. Therefore, minus x dot of 0 plus s times minus x of 0 plus s times L of x. So rewriting x equals the Laplace transform of x again, okay, we can say that this x double dot becomes minus x dot of 0 minus s x of 0 plus s squared times x. Then we go for the s dot part. It would be plus 2 times, well, x of 0 there's a minus in front of it. My mistake. So we erase here and there. And we go back to minus 2x of 0 plus 2sx plus x, this guy, is equal to 0. Okay, let's do an artistic separation. We can even plug in the numbers, so it becomes like minus 1. Sorry, that's x dot of 0. So that's minus 3 minus s times x of 0, so minus s plus s squared x minus 2 plus 2sx plus x is equal to 0. Or we can factorize the x and the s's and we obtain like 3 minus s minus 2, so that's minus 5 minus s plus x. Okay, so let's face it, my 5 looks like an s and my s looks like a 5 plus x times s squared plus 2s plus 1 is equal to 0. Now what is this? Aha! This is, in other terms, getting us to say that x is equal to 5 plus s divided by s squared plus 2s plus 1, and that's s plus 1 squared. Okay. So as long as we can compute the inverse Laplace transform of this, we're fine. Do we have it? No. If you remember, we have things like these. 1 over s plus 1, we know that goes to e to the jt. 1 over s plus 1 squared, we have that as te to the jt. But that is not exactly this. So what we have to do is make this look like a sum of those. Okay? So we're going to erase this. And let's Let's see what we get. Ta-da-da-da. If we erase this decently enough, okay, what we're going to do is we're going to write and do the complicated operation of finding A and B such that 5 plus S divided by S plus 1 squared up is equal to A over S plus 1 plus B over S plus 1 squared. It's very easy. We reduce that to the same denominator. We get A times S plus 1 plus B must be equal to 5 plus S. Immediately that tells us that A equals 1, and if A equals 1, B equals 4. And we get that this expression is, so x, which is 5 plus S divided by S plus 1 squared, is equal to 1 over S plus 1 plus 4 over S plus 1 squared. And therefore, we can immediately find out what x is by simply, first of all, cleaning this up, cleaning that up, and using this and that. If this is the Laplace transform of x, then that means that x of t will be simply e to the j, e to the t, not e to the j times t. Okay, that's a mistake here, and that's there. So let me rewrite this as e to the t plus 4t times e to the t. And that is our answer. All right? So, yet another case where we can very easily solve the differential equation using only the Laplace transform. Now, what we will see is that there are tons of these things that we can do. Okay, it's endless. And I just want to show you some more stuff about solving differential equations. So far, what we have was what we call unforced differential equations. Okay, they only this x dot, x double dot that appear. But what if instead we had a forcing term, say a step? We would like to know how the system reacts to a step. Okay, so for that, what I'm going to do is clean that up and rewrite the system. For the sake of keeping things simple, we're going to use just the step and no initial condition to begin with. The differential equation, if you remember well, was x double dot plus 2x dot plus x was equal to 0. Now we'll change that. We'll say it's a step. Okay? Like what we've seen a couple of lectures ago. Then in this case, again, we go into the Laplace domain. Here, to keep things simple, what we'll do is we'll make sure that the initial condition, x of 0, x dot of 0, are 0. Okay? So what that means is that we don't need to use anything else but say that this is just s squared x plus 2sx plus x, and we don't have to put the initial condition there, you will see in the future that this happens more than often, is equal to a Laplace transform of step. What's the Laplace transform of step? 1 over s. Okay. So very quickly, what we get is that x time must be equal to 1 over s times 1 over s plus 1 squared. What is that anymore? Well, what we're going to do is going to write it as a couple of things. Something involving 1 over s, something involving 1 over s plus 1, and something involving 1 over s plus 1 squared. Okay? So let's solve this for a second. Okay? We're going to say this is c over s plus a over s plus 1 plus b over s plus 1 squared. What does this give us? Well, we put everything to the same denominator, and we obtain that we can have c times s plus 1 squared plus a times s plus 1 plus bs divided by blah 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 blah, the product of these things. So this top thing must be equal to 1. Alright, so we go and equate the quantities like we've done before. Okay, so let's look at the terms in s squared. Okay, in that big expression. S squared times c plus a. Then we have the terms in s, which are 2c plus a plus b. And then the constant terms, which are plus c, and then nothing. So we know c must be equal to 1, because that's what we need. Now if c must be equal to 1 and c plus a must be equal to 0, that means that a must be equal to minus 1. Now 2c plus a plus b must also be equal to 0. So 2c is 2 plus a is 1, so that's 1, and so you get that b equal to minus 1. Okay? Alright, so now we're back to our differential equation, and we can do a serious amount of cleanup. Okay? And because we pretty much have everything here. Okay? So if this is x, and we have as values for a, b, and c, let's see, 1, minus 1, and minus 1, okay, then we know that x of t is simply going to be equal to 1 over s minus 1 over s plus 1. Oh, sorry. Let me redo this. I want x. I'm in the time domain. I'm not in the frequency domain anymore. So we have x of t is equal to, well, the inverse Laplace of c over s, or 1 over s, is going to be step. And then minus a is going to be minus e to the t. Minus t, to be more precise. And then this guy puts b, minus t, e to the minus t. And that's it. By the way, here is the graph of this. That means that we actually do have the response of a very interesting differential equation to a step. We will see that over and over again. Oh my god, this is so hard to use. We will draw the two axes, okay? And we have a step. So here's the step coming into action. And the step was like, and then boom, and then like this, okay? And the response of the system is something like this. Up, and then like that, okay? So it looks like a step and eventually becomes a step because all these terms go to 0. It goes there asymptotically. It's like a smooth version of this. And this is why this differential equation, we will see that later, can be seen as a filter. It takes the step here and smooths it out. That's what a filter does. It takes the good stuff and takes away the harsh stuff. Okay? That's why you need a filter to make good coffee. Okay? This is coffee. This is filtered coffee. It's much smoother. Very good. I think this is good enough for today, and we will restart in the next lecture. Thank you.